Greetings, Earthlings. I can see NVIDIA wants me to use their in-game overlay. Uh, Today I'm just going to be showing off this little tech demo that I made in my spare time. The concept behind this is very simple. I was watching a video where they showed some sodium vapor lights, and my thought was, okay, it's interesting because you can't actually make those in a standard game engine because they put out a monochromatic frequency that a computer doesn't simulate. So this is just a quick demonstration of some of the various things that we can do if we have 6 channels of color instead of 3. So what I've done here is I've taken the entire scene, and this entire scene is actually in the background being rendered twice. So, I'll just sort of look around, you get a bit of a preview of what's coming. But the whole scene is being rendered twice. Once to render the RGB channels, and once to render the YCV channels. And those are then being composited in post-processing. One note about the implementation, by the way, is that rather than have 2 different cameras, this current implementation, this particular demo, is actually just rendering RGB on odd-numbered frames and YCV on even-numbered frames. So it doesn't just effectively have the frame, it actually does have your frame rate. And the reason why I'm doing this, this is a bit of a tangent, so skip ahead if you want to see me just go around and play with all the buttons and stuff. The reason why I'm doing this is because I tried programming it with a, with 2 cameras, and for some reason, Unity just was not cooperating, and I already had everything working with a single camera and the alternating frames approach. That being said, I think in a sort of more polished final game kind of project, you would definitely want to get 2 cameras to work, because the issue that you get with alternating frames is that in some cases the two sets of channels end up out of sync with each other. By the way, one other thing I will say on the implementation side of things is that it would be really nice to just be able to render the scene once, but as it stands, I think basically any modern graphics pipeline is going to assume that colors have, 3 or 4 channels. So we'd be at the level of having to not only replace the game engine, but having to write custom sort of modifications to DirectX or Vulkan or OpenGL, whatever the underlying graphics library is. And it might be that the hardware is not optimized for operations that aren't based on a 3-color system. Admittedly, I don't know much of the internal details of GPUs. Maybe in the future somebody will come up with a more than 4-channel rendering system as some kind of particularly experimental addition to HDR rendering, because that's effectively what you're doing in HDR. Is you're taking the data type of a pixel and you're replacing it with a different data type, but usually the length of the vector isn't included in that. So, alright, so enough jargon. Let's talk about how this actually works, and what this actually does. So right now we've got what's called normal lighting, and this light is putting out all 6 channels. And so what that means is that we have, red, green, blue are set to 1, yellow, cyan, violet are all also set to 1. And now, this means that if we take a picture like this, this looks normal. And now what I'm going to do is this button here demonstrates what happens if we're only viewing this through the RG and the B. Now, I want to clarify that this isn't, oh, we've just gone back to RGB rendering. The rendering is actually always 6 channels no matter what, and the materials are going to account for that. What we're doing here is we're simulating what RGB-based lighting might look like in a world with more than 3 colors of light, which of course is our world. And as you can see, it still looks all right. You can still see, you can still tell what's going on, but there, the rainbow here does not look correct. There's just differences in various colors and whatnot. One slight inaccuracy here, in actuality, it probably wouldn't look this bad, because, well, I'll explain why later, but point being, the pigmentation of everything here isn't necessarily 100% accurate either. So I mentioned earlier that you can't have a yellow light with RGB. You can't have a monochromatic yellow light, and here's what happens when you try to have a yellow light. So this light is now putting out yellow, but it's dichromatic yellow. It's part red and part green, which is what yellow light is going to look like in any, in a standard game engine. You can see red things and green things in addition to the yellow things in between. By contrast, here's what an actual sodium vapor lamp would look like. Everything is just yellow. And this is actually, from what I've heard, a fairly spectacular effect to see in person. So if you have any opportunity to just look at things through a sodium vapor lamp, I would recommend it. I've seen some videos on YouTube, but a lot of them make it clear that, hey, no, in person this looks a lot more interesting. By the way, you might notice that these buttons aren't quite yellow. That's because the buttons actually glow slightly. You'll see that more obviously later on. Now, one objection you might have to the notion I keep spreading that, oh, you couldn't do this with RGB rendering is, well, couldn't you do it in post? And yes, no, you absolutely could do it in post. And you can do that if every light in your scene is a sodium vapor lamp. But if I want to, say, add a flashlight that shows true colors so that you can only see the colors in areas that are lit by this sort of light, that's something that's a lot trickier. That's something that you're not going to be able to do nearly as easily with post-processing, and the complexity of this, like, if it's just a one-off effect, I get it, but if this is a scenario that's going to occur a lot throughout the game, I would actually, recommend having a 6-channel rendering system. I think that's one of the potential applications of this. Another thing that we can simulate more accurately with this kind of light is what happens when we go underwater. So what I'm doing right now is simulating the effect of being 10 meters underwater. And that was computed with, I referenced some actual tables of water absorption. I haven't really had much of a chance to compare this to what light 10 meters underwater actually looks like, because, well, honestly, that would be very tricky to do. You would have to, you'd have to mess with gamuts. You'd have to worry about all sorts of other things. This is all just sort of approximated because there's a whole lot more to color science that I'm not going into here. But anyway, if we move to 100 meters underwater, you can see that things get really blue, which, should make sense. That's how water generally works. And if you look over here, you'll see that you can still see yellow to some extent. It's hard to tell, but it's not completely green per se. However, red is basically right out, right? You can't really tell that red is here. So again, it's definitely subtler, because you could definitely get something that's passable for this effect with just RGB, but it's just a little bit more realism once you have the 3 extra channels of light to work with. By the way, you might notice that those things aren't changing color, and you'll see why in a bit. So sort of the second wall of this gallery, it's sort of organized by wall. This one talks about different colors of light, and this one's going to talk about different colors of paint. Now, because we're now working with 6 channels of light, we also need 6 channels of paint. And this is honestly, I think, one of the biggest hurdles to creating a, 6-channel system for a full game's worth of content, is that not only are all of the rendering pipelines built to assume 3 channels, so is all of the image editing software that exists, basically. It's possible that someone has some, GIMP plugin or some such that will do this. It might be supported in, Photoshop if you give Adobe your firstborn child. I don't know. But what's much more convenient is to have a situation where we can take a material that's in RGB color and convert it to one that has all 6 channels. And now the algorithm that I'm using for this is actually extremely simple. It's just taking parts of the RGB pigment and shifting them over. It's just a little bit of linear algebra. And it does have an unfortunate effect, which you're going to see here. So the top one here, this only has RG and B light reflected. It absorbs all of the Y, C, and V. But it looks identical to the bottom one because, of course, that's sufficient. YCV alone is not quite sufficient because of the fact that, the gamut no longer matches what your monitor is able to output. So if you take a look at RGB only light here, you'll see that the top one still looks just as vibrant. The bottom now, the yellow, cyan, and violet are no longer as vibrant as the red, green, and blue. That's the same effect we saw with the rainbow over there. And if we move to a YCV light, you can see the YCV is just as vibrant. But now, here's the tricky thing. Because of the way the light colors combine, if you were to simulate, for instance, red with yellow and violet, there would always be some amount of white sort of added to it. It would always be a little washed out, which you can see up here. And what that means is that if we want to guarantee full fidelity for our usual textures, when it comes to pure red, we can't be converting any of that to YCV, which has the unfortunate effect that the red in a sort of mixed texture, when we do it the fancy way, it just doesn't show up in YCV. Anyway, so over here we have this neat effect. So there are 2 different types of yellow paint in this image. You can probably see the secret message already because I didn't put a ton of effort into making it seamless. But one of these paints reflects yellow, and the other reflects red and green. And the result of that is that if we change our light frequencies, we can have quite a dramatic change in the colors here. So you can make things that are hard to see unless you're using light that isn't balanced in that regard. And this is an effect that you can't really get with 3 channels again. With 3 channels, everything is 1-to-1. Every color that you can see corresponds to exactly one representation of that color internally. But YCV isn't like that. YCV has different representations of what will look like the same color. And so we get this effect. By the way, this is also a place where the effect of the frame interleaving becomes most apparent, because you can really see these fringes that pop out. That's honestly really ugly, and that's why I would highly recommend that people actually do it properly with one camera rendering, or with 2 cameras rendering at the same time. So then this last thing's a demonstration. This isn't really an effect of the 6 channels themselves. It's more of a side effect that I've managed to program as well. And that is a shader that simulates fluorescent light. So right now, all of the light is violet. but violet light is, of course, very energetic, so it's able to stimulate these fluorescent pigments, just like you've probably seen in blacklight photographs. You have a nice sort of fluorescent orange, a bit of a chartreuse color, and a sort of sky blue. In the code, these are called orange, lime, and azure, and you can combine them. So they're another 3 dimensions of color, so that this type of paint actually has 9 dimensions overall. Now, one thing to note is that this is different from the buttons, which actually glow, in that these pigments can't produce light unless they're given light. So if we put ourselves into total darkness here, now you can see this this isn't actually giving off light, but with the violet light, it's able to absorb that and re-emit it as a lower frequency. Now, one thing I should point out here is that, just a little bit more of a behind the scenes, I had to do a lot of work on the shader end to get this to work, because another assumption that graphics pipelines tend to make is that the light color gets multiplied by the paint color. And that's still somewhat true when it comes to fluorescent paint. The difference being that fluorescent paint ends up converting one channel of light into another, so effectively, fluorescent light, instead of its color being a vector, its color is a matrix. And again, that's something that is obviously enough of a special case for there not to really be support for it out of the box, but it's something that I kind of wish more graphics libraries and game engines could support, at least on some level, because of the really neat and quite realistic effects that you can get from it. Speaking of effects, let's talk about this last wall. The fact that we have these 3 extra channels of light to work with means that we can enhance the quality of image effects. And a great example of that is what's known as chromatic aberration. Chromatic aberration is the fact that a lens will inevitably refract different frequencies of light to different degrees. And this normally isn't visible, but on the borders of a particularly sort of prominent lens. What's the word for that if it's really curved? Anyway, the fringes definitely are going to show some chromatic aberration. And so, here's what a very basic chromatic aberration effect looks like with RGB. Now, again, we can't actually have RGB because we don't have, because we've converted the entire rendering system to use 6 channels. So we're simulating RGB here. But as you can see, on the fringes of the image, we have the colors changing, right? But with this kind of effect, you don't get the sort of smearing that you normally get with real life photography. Real life photography, you don't have distinct images here unless the light that's being aberrated? What's the verb there? Unless that light is itself monochromatic. But here what we get are these effects where we have essentially 3 images of each object. And just for the sake of completeness, here's what the same thing looks like with just the YUV channels. And one thing to point out is that, as this sign says here, we could just blur the edges a little bit as well to make those color transitions smoother. And that is a valid way to solve this problem. And it's what I would expect any, sort of standard chromatic aberration effect in a game engine to use. The problem with that, well, I guess the first problem with that is that blurring is generally a fairly expensive effect in terms of real-time graphics, but that's fairly easy to get around. The bigger issue is that the color accuracy is lowered. And specifically what I mean by that is that if you do have monochromatic light, it's still going to get blurred by the chromatic aberration when it really shouldn't be. So over here, this is now 6-channel chromatic aberration, and you can see the effect looks much better. Now, you do still get some degree of individual images, but because there's 6 of them instead, instead of 3, it looks a lot smoother, and in my opinion, a lot more realistic. Like, looking at this, there's also a bit of a glitch in this shader, but don't worry about that. If you look at that looks like a gradient there. That doesn't just look like individual images. So, I think that with the 6 channels, you overall it ends up looking pretty good. And again, you could do blurring to remedy this, and even if you are going to blur it anyway, 6 channels is better because you only have to blur it half as much. So, those are all the sort of basic demos here. That being said, there is one more thing that's in this demo. I'll release all of this, by the way. There's a link in the description if this is up on YouTube now. There's a link in the description as to where you can, download this demo and play around with it yourself. And if you want to play around especially much, you can come over to the Playroom here. So here we have 3 tables and some objects on top of these tables, and everything here has a customizable color, as well as these 3 lights that have customizable colors as well. Right now, the basic demo is that we have violet light stimulating these 3 different fluorescent pigments. But we can come over here and we can really modify that a lot. Here, let me quickly do one demonstration that I really like to do with this, which is to turn these lights down from violet and instead just have a top light that's pure white. And so, this is what everything just looks like with white light above it. And then come over here and keep the skull as is, change the colors of Cyan and the T-set using red and yellow pigments instead of the fluorescent orange. And you can sort of match these swatches here to sort of try to match the colors as well as you can. And then you can come over here, and all 3 of these objects now look a pretty similar shade of orange. I think Cyan needs a little bit more. I probably need to bring down the skull a little bit, just because the, Yeah, so these all look pretty much the same shade of orange. And you can show this to your friends, and you can play the little game of, okay, guess which one of these is a different type of orange paint from the others. And then when they have no idea, all you have to do is turn up the violet light on the left and right. And you'll notice that, well, it's actually a little hard to see here. I guess it's easier to see if we also turn the top light down a bit. So let me turn the top light down to sort of half of what brightness it was at. There we go, and you can see now that the skull is much brighter than the others because it's also being, it's also fluorescing in addition to having its standard color. And lastly, of course, we have the chromatic aberration lens if you want to see the effect of that as well. So you can do things like, for instance, actually, here's an interesting effect that I just thought of. You know what? We're gonna do some live messing around here, some live experimentation. I'm going to take the top light, turn it all the way up, and now we get this this chromatic aberration effect. And now what I'm going to do is this. I'm going to turn all of these objects yellow. But the difference is going to be that the skull, I'm going to make pure monochromatic yellow paint, and then these others I'm going to sort of combine these paints. That needs to be a little brighter. That's a little too bright. That looks about right. Same for the T-set now. And now, as you can see, these all look pretty yellow, you know, the same sort of mustard yellow color. Suzanne doesn't look bright enough. I'll just turn up her own yellow channel. There we go. But now, if you look through the chromatic aberration, oh, that's actually really neat. So you see the T set there has all this chromatic aberration of it, and same with Suzanne, but the skull is actually completely immune to chromatic aberration because it only has one frequency of light it's reflecting. So there's no smearing effect. So that's that's actually a really neat example of why the chromatic aberration effect depends on the number of channels. It's subtle, I'll admit. It's subtle, but you could really do this to some sort of effect in a game if you want to have some element that really pops out, like a sort of cinematic effect. Obviously, it's one of the reasons I use the skull for these demonstrations is because it's a little bit frightening to have the skull be the thing that really pops out at you. So yeah, that's about really all I have to say in terms of this this little demo here. Again, it will be available for download in the description, so you can play around with it yourself if you like. To be honest, I should probably share the source code for this as well at some point. I'll have to look into that because it's entirely possible that I'm using some kind of asset that prevents this, or that there's, you know, something in here that's like a spoiler for filtration or something. But I'll look into that at some point, see if I can release the source code. I mean, it's a pretty simple effect, to be honest. Really, really the only main thing is knowing how to combine the colors when all is said and done, and knowing how to modify materials. But all of that, I think, if you're an accomplished programmer, you can sort of just trial and error a lot of that. And you need to know a little bit of linear algebra, but of course, you probably need to know that anyway for anything computer graphics related. So yeah, I think I'm going to end things here. Thank you so much for watching, and I will see all of you Earthlings, another time.